Perfect. Ryan, I can see your slides. You look ready to go. Yep, Ryan Lau is here to teach
Yep.
us all about difference images and light curves. So take it away.
All right. Thanks, Melissa. And yeah, thanks everyone for tuning in. So I'm Ryan Lau. I'm a staff astronomer at NORLAB on the Rubin Community Science team. And in this session of our Data Academy, we're going to be talking about difference images and light curves. So if you just joined, you probably don't see the link to the slide, so I'll send it again in the chat. There you go. So if you want to follow along, which I recommend because for some of the portal queries, you can copy and paste some of the text there. And I think some of us will also be able to paste it in the chat too, so you don't need to worry too much about that. Okay, so just some introductory stuff. For those of you who are just first attending to this session, welcome to the Rubin Data Academy. As I'm sure you may be aware, this year is a little bit different. This is more focused on kind of beginner level use of the Rubin Science platform and excitingly accessing the Data Preview 1 data products. So actual data products taken with Rubin, which is pretty cool. So if you've attended this before, like in the past couple of years, they're hack and networking sessions, but we've now replaced them with Q&A sessions, which you can see here in the schedule at the times there, and those are all in Pacific time. So there's 10 sessions that are kind of running, and there's concurrent sessions that are also running. So as Melissa was mentioning earlier, there's a breakout room that's now going to talk about getting started with the RSP. So if you're looking for just a really like you're diving or jumping right in as a beginner for figuring out how to get started with the Rubin Science platform, definitely go to that breakout session. And then you can always tune into this one either in a recording or tomorrow at the same time in the breakout room, as you can see here from the schedule. But just to give you all heads up, this is where we are now in the schedule. So this is the session um, that we're currently in. And so there's a bunch of Rubin staff here on the community science team who are supporting this data academy. And so if you can ask questions in the chat, or if you want to ask a more immediate question, feel free to raise your hands. We'll kind of be monitoring that as well. And then if you have a question later on, like if you're reviewing the recordings or you have something that came to your mind after the presentations and the tutorials and everything, definitely go to the community forum, make a new topic, and go to the support category. This is essentially like our help desk. And so we're all monitoring it very vigorously because we want to make sure that everyone has the right answers to help enable and support their science. So you would just go to the support category, write your topic here, and make sure you have the context to it so we can best help diagnose any kind of issues or questions that you have. And also, as a reminder, so everything in today's session in the Data Academy, it's going to be available on the Data Preview 1 documentation at this link here. So again, if you have any questions like about what's been covered, what the data products are, I highly recommend checking this out. For citing Data Preview 1, there's a DP1 paper, and you can access that through this link here. It has the relevant like DOI identifiers to use when you want to cite this data set. So check that out as well. It has a lot of important information. And it's in this, yeah, in a paper version. And for general information about Rubin, check out the For Scientists page of the Rubin Observatory link here. Okay, so we're just gonna go right in to the topic or just an overview of what exactly we're doing here in this session, session number 9. So we're gonna be going over essentially time domain astronomy here. So transients and variables and the relevant data products, which will be difference images and how we plot light curves and the data products relevant for plotting those light curves. So what we're doing here is a kind of a hands-on tutorial about difference images and the associated tables with these photometric measurements for difference image sources. So DIA is an acronym you'll see quite a lot. And the tutorials that we're going over today, we'll do some more hands-on ones with actual science use cases. So what was cool about DP1 with the LSSD ComCam commissioning run is there was actually a supernova or supernova candidate or some kind of transient that appeared here in this galaxy in the ECDFS fields. So this is like the what's called the cutout triplet. This is the science image, so a new image that was taken, a reference template, and then the difference image. And you can see that transient pop up there, and its host galaxy just disappear in the difference image. So we'll go through a notebook that shows that. We'll go through a notebook that also goes through how to best practices for plotting a light curve using forced PSF photometry, which is on the force source on DA object table. So those will be the topics of the notebooks here. Before we get into that, I'll go through more background on the actual data processing. So how we go from science template and template. I just realized I spelled template wrong here. I'll have to fix that later. And then the difference image. And so this is all done with what's more broadly called difference image analysis. So you'll see this acronym a lot, DIA. Sometimes it's capitalized, sometimes it's not. Like in the table here, DIA is lowercase, but it all kind of refers to the same thing, like difference image products or difference image analysis. So those are all products of these difference images here. So the data products, you can actually access the difference images in DP1. And then there are catalogs that come from the analysis of these difference images. We have DIA sources, DIA objects, for source on DIA objects. And so those are the data procs we'll go over. And then we'll jump into the different tutorials that we have. So using different aspects of the RSP, we'll use the portal, showing how to display a difference image, how to retrieve and plot a light curve, and then kind of as I mentioned earlier, notebook tutorials on how to do this stuff in the notebook environment. Okay, so I kind of mentioned this a little bit in the previous slide, but some key concepts to keep in mind when we're working with difference images and trying to plot light curves, studying transients and variables. Um, some of the key terms are template coad images, uh, doing image subtraction, difference images, and this DIA acronym, which I described in the previous slide. So this template coad image, it's going to be a combination of a third of the best seeing visit images. So that's what's used to build this reference template to do the image subtraction. So it's how to identify all of the variable time varying things in the sky at that specific at these different pointings or different fields. And so that's what happens next. We do an image subtraction. So a template, which is built from these best seeing visit images, is subtracted from a new visit image, and also the previous ones, to create a difference image. And then again here, just a reminder, difference image analysis, DIA. All right. These terms here, DIA object and DIA source, while they kind of sound similar, these are different terms. And so this is the specific definition of what a DIA source is and a DIA object. So this is pretty much analogous to the source and object tables, except instead of on visit images, these are done on difference images. So a DIA source is a detection of a 5 sigma detection of anything in a single difference image, whereas a DA object is kind of the actual transient or variable at the static sky coordinate that's associated with that DAA source. Um, so a DAA object will have uh, multiple DIA sources associated with that DIA object. And then the type of photometry that's recommended to use for plotting light curves is going to be this forced photometry. So that's essentially a forced measurements, PSF measurements at the coordinate of that DA object in a difference image or a non-difference of visit image. And that's done regardless of the threshold of the detection of that DIA source. So you could have like your transient or variable may not have been fluctuating in one of the visit images where a DIA source was not found, but force photometry will run at the position of that DIA object, whether it's anything that's kind of plus or minus 5 sigma. And so you get a detection or a possible detection of that there. It'll just be below 5 sigma if there's no detection there. And then I'll be mentioning light curves a lot. And so that refers to that plot like I was showing in the previous slide. So either transient or variable that brightens or fades over time. And usually it's plotted in magnitudes or flux versus time. So in the plot that I was showing here, it's MJD on the x-axis and then flux units on the y-axis in nanojanskis, are the units that I believe the image data products are provided in. And it is highly recommended to use this force photometry for light curves. And because you can get negative fluxes, as you can see here in this light curve, it's recommended to use flux units here. You can convert to magnitudes, but then it's difficult. You can't really convert negative fluxes to magnitudes, so you'll lose out on some information there. Okay, so how exactly does this data processing work for difference image analysis? So a little bit more details here about how the difference imaging is done. First, there's this after a visit image is taken, so that's like a new image that's taken. You have your template that's built again from the best seeing visit images that's warped, scaled, and PSF matched to the visit image. So you try to make like a perfect match from that template image to the new image. And then there's an implementation from this Allard-Lupton algorithm that's used for the PSF matching, and then the subtraction that takes place between the visit image and that warped, scaled, PSF matched reference template to subtract to get your difference image. And you have one of these per detector per visit. So pretty much for every visit image, there's going to be an associated difference image with it. And so the visit IDs should be the same. The detection, so what counts as when you detect a DIA source or not is positive or negative sources in that difference image with a signal to noise above 5. So that's what counts as if that gets identified, then that gets cataloged as a DIA source. It gets like a DIA source ID, and then a bunch of different properties are measured from that source. So those, yeah, PSF fluxes especially are measured for all those detections here. The way that the association works, so you have these DIA sources that are found in every difference image. You're going to want some kind of mechanism to associate it with a particular transient or variable, and that's what's kind of grouped into these DIA objects, like I was mentioning earlier. So everything within 1 sigma of a DIA object, like any kind of DIA source that's found within 1 sigma of a known DIA object, gets associated with that. So a DIA object will have a bunch of DIA sources that are kind of yeah associated with it. And the products that include that data or that this information are the DIA source and DIA object tables. And so, as you can imagine, there's going to be a lot of, if you're trying to plot light curves or look at data products associated with any time varying phenomena, you're going to work with both of these tables here, DIA source and DIA object. And then, kind of like I mentioned in the previous slide, there's force photometry that's done on all the at the locations of all the DIA objects, in all the visit images and difference images. And the product from this is a force source on DIA object table. And that's what you want to use to plot your light curves, since that'll have the most information. So this is an important table to use for plotting light curves. All right, so we're going to jump into a little bit more of a description of the data products. So difference image, if you want to grab a difference image, you can do it in a couple different ways. You can use the butler. You can write a butler query and grab difference images from certain coordinates or certain properties based on what you want to access or what kind of images you want to access. There's the simple image access service, or SIA, which you can use to obtain the images. And then there's also a table access protocol service that you can use as well. So all of these have kind of different ways to obtain the difference image. Um, and depending on your use case, you might prefer one over the other to do it. But there's similar ways to access this particular data product with these three services. If you're using the butler, this is what the kind of the product is called, difference underscore image, and then you give it like a band, the instrument which is just LSS TCAM. You can give it the day observed, detector, the physical filter, visit, and it's in this file format, what's called exposure F. That's just giving you an idea of what the data set type is in the Butler for difference images. So that's very similar to also visit images as well. The calibration level for difference images is level 3. Um, and so I think that's just essentially, it's just taken one step further from the visit images. So visit images or non-difference images, those are level 2 calibration levels. If you're doing a tap query for difference images, you want to use this ivoa.obscore table. And then we'll demonstrate an example of writing a tap query in the portal to obtain a difference image using this table. That's why that's provided there. And then this is just showing you the number of difference images in DP1. So there's a lot. The actual data of difference images, again, very similar to visit images. You have the image plane, which is sky pixel data in flux units of nanojanskis. There's a variance plane, which is kind of the uncertainty or noise in units of nanojansky squared. And there's a mask plane that has integer values that flag any kind of issues or maybe weird stuff that's going on in the image. Also, I think it also shows you can also have it show sources that are detected. So not just weird stuff, but important information about that particular image. There's all any kind of probably any kind of metadata that you would want are inside the headers. So you can check out like the weather conditions. You can grab the PSF kernel of the difference image. It has the photometric calibration that was used, WCS. So all of the important metadata that you would need to understand the conditions and the way that these images were produced. And then if you have a question about the tap schema, you can check out this link here. Okay, so the DIA source table, this can be accessed using the tap service or the butler. If you're doing a butler query, it's DIA underscore source. You give it a sky map, where's your sky map, and then a tract. So currently, I don't think there's a way to do this by visit ID or anything. But you could do this if you only care about what part of the sky you're looking at and do a butler query there. Um, Probably the more recommended way to access the DIA source table might be through the TAP service, and this is the name of the DIA source catalog using the TAP service here. There's 87 columns, so there's a lot of different properties that are given in the DIA source table, there's a ton of entries here. So 3 million, over 3 million entries in the DIA source table for different detections on different 5 sigma detections on the difference images. An example of some of these columns. So, there's 87 of them, but these are probably some of the more important columns to keep in mind when you're accessing this table. Each DIA source has a unique ID, which is called DIA source ID. It has the associated DIA object ID. So you can have like a bunch of DIA sources that are linked to the same DIA object, and that's how you would kind of help build your light curve or find how many sources were detected of a particular object. Also, if it's a solar system object, it gets a solar system object ID. So that's kind of one way also to see if it's associated with the solar system object. And that's also provided in the DIA source table. It has all the relevant visit information. So the visit ID is, the detector, the filter or band that was used for the detection, and then this midpoint MJD, um, the essentially the filter or the exposure time midpoints of the detection or the visit where the detection was made in the difference image. And then importantly, coordinates, PSF flux, science flux. So this is just difference image flux and the actual visit image flux is science flux. There's a couple of important flag columns too, like is dipole. This is important because um, if you have like something weird going on, like a bad subtraction between like your reference template and a difference and their visit image, you might see like a positive negative um, source looking thing pop up in your image or in your difference image. And so there's an algorithm or routine that flags whether or not that dipole is there. And if it's there, it's probably an artifact. So you can use that flag to help filter out some junk. Um, I just realized I raised my hand. I have no idea how I did that. Um, and I don't know how to put it down. So it's probably just going to be up there. But yeah, again, yeah, if anyone has questions too, feel free to raise their hands. Okay, there's a DA object table, which can also be accessed through the tap service and the butler. Here's the butler information of it, very similar to the DIA source one. The name of the table in the tap catalog or the name of the catalog in the tap service. The number of rows here, so you can tell this is less than the number of DIA sources because these are just the kind of like the coordinate, those positions associated with an object. And then here are the kind of key columns here for the DIA object table. Most of it is like flux characterization parameters, like what is the minimum flux that was observed from this DIA object? What is the maximum flux? What's the mean flux, the sigma? And things also like the slope. So there's other flux characterizing parameters in that DIA object table from the DIA source fluxes that were associated with it, or DIA flux property, source properties that were associated with it. It also has the number of DIA sources, so that tells you like how many DIA sources were actually associated with it. So that yeah, that helps too when you're looking for things that are detected for more than n number of times, which can help make sure you're detecting something that's a real time varying source. And that's not just detected like NDIA sources equals one. So that's one way to kind of rule out any kind of noise or um, uncertain kind of variability. All right, and then there's a force source on DA object table. Yeah, again, you can use the butler or tap service. It's like almost 200 million rows, and that's because this is like force photometry at the position of every DIA object on all the visit and difference images. So this is a pretty um, lengthy catalog and it has you can associate it with the DA object ID. It has all the visit information on it, the coordinates, and then the fluxes. And so each entry in this force source on DA object table is on essentially just one DIA or a measurement in a difference in visit image. So that's why there's so many of these, um, or there's so many rows in this table. Okay, so I can pause here a little bit and take any if there's any questions so far on all this stuff that I went over because we're going to jump into the portal tutorials after this. So I can see if anyone has any questions. Uh, yeah, Naoki, if you wanted to unmute, feel free to
Yeah.
do that.
So DIA object is defined even if there are only one DI source, or do you require some uh, two detections or something like that?
Let's see. DA object. Yeah, so okay, yeah, good. I think I understand your sort of question. So let me repeat it. So you're asking um if a DIA object requires a certain number of DIA sources to create a DIA object?
Yes.
Yeah, okay, good question. So, um, anytime there's a DIA source that gets made that is not associated with a DIA object, a new DIA object is created.
Oh,
So,
I see.
if there's, so you have your new image taken, you take a difference, and then there's something else, there's something that pops up, there's a transient that pops up in some region of that detector where no other DI object has been seen before, where there's no other type of time varying activity has been seen. It gets flagged as a or detected as a DIA source if it has a 5 sigma difference or 5 sigma significance in the difference image. And it looks for any other DIA source in a 1 sigma or 1 arc second radius. And if there isn't any, yeah, then that DIA source, then a new DIA object gets created. So there's no threshold for creating, there's no DIA source number threshold for creating a DIA object. So you can have DIA objects with NDIA object equals one, essentially. Yeah, or NDIA sources equals one.
And so you are not sorry, you are not setting any screening to get rid of artifact or something like that. The
So
source includes everything detected.
So there are flags in the DIA sources.
Mhm.
So if you wanted to, you can use the flags that are provided to filter out, um, let's see what DIA sources you can use. Or if you're looking through the object table, if you want to ignore what might be noise, you can just make sure that all of the DI objects, or when you're querying the DI object table, you're ignoring things with NDIA sources less than like two or something. Or you can set some sort of threshold
I see.
in your query to reject anything with a low number of DIA sources associated with it.
I
Which
see.
is might be a good thing to do to yeah to get rid of the noise or anything that's yeah that looks weird.
Okay, thank you.
Yeah, good question. Thanks. Okay, I'm gonna move on here to the portal tutorial. So this will be pretty straightforward. What we're just gonna do is we're gonna display a difference image. We can actually look at it and see what it looks like. We're gonna use an ADQL query in the portal to grab this image difference image that's at the center of the ECDFS field, which is a pretty was one of the heavily visited fields in DP1. So what you can do is you can, if you have the link to this, or I can also copy it and then paste it in the chat. I'll put that here just for now. And what you're going to want to do, oh yes, and I see a question was EM min and EM max. So I believe that's you can specify the wavelength range um, of like the image that you're looking for. I think that's what it corresponds to. There's also a schema directory that tells you this. From my understanding, if you want to grab an R-band image, you're going to look at 622 nanometers, uh, and that's how you do the query here. I think there's no easy way, like you don't say I just want R-band images. I think this is the way you specify um, what filter you want to look at using this particular portal search. So this is good for just like grabbing images or just viewing images. But if you wanted to do this a little more uh, rigorously, you could use I would suggest using the notebook aspect or perhaps doing a different search. Um, but we can actually take a look at that at the actual definitions of EM min and EM max as we go through this. So let's go to data.lsst.cloud. So that's our RSP website here. So I'll just do this again. Make sure you're logged in. And then we're going to click on the portal aspect over here on the left. And then you'll see the portal landing page here. What we're going to do is going to go to DP1 images on the top here. So this tab that says search DP1 images. And then we're gonna we're gonna ignore all of this stuff here for now. We're gonna go to this top right here and say do edit ADQL. And essentially you can do the same query that I just pasted there using these properties here. And since there was a question on EM min and EM max, uh, it says here these are start in spectral coordinates and stop in spectral coordinates. So yeah, I think those are just the wavelength values in meters. So that's why it's the ADQL search has 10 to the minus um, or 622 times 10 to the minus 9. Okay, so what I did is I just clicked here, edit ADQL, and you can switch between the UI assisted view or the edit ADQL view. And then we click on edit ADQL. You can copy that code that I pasted into the chat there, and then just paste it in here. So I'll clear it again, and just to show where I'm putting it, you just paste this here exactly how it's copied. And then what it's going to do is it's going to grab um, all of this info from the difference image in the obscore table. And so this is the obscore table I was mentioning because we're doing a tap search. And it's going to search this region in the ECDFS field. So these are the coordinates in degrees. And then it's going to grab an R-band image, calibration level 3. And then we're making sure that it's a difference image that we're obtaining in this search. And so on the bottom left, you can click search, and then it'll do the search there. So we just got to wait a little bit. And then here it is. So here's the difference. Here's like a detector uh, of the difference image from a detector here for these observations. And then you can see this whole table here of all of the difference images that were found in our search. Um, and then over here on the right, there's this kind of scatter plot of the difference images that you can actually click on too. So if you wanted to see a different one, you can click on this. I was playing around with this earlier, so it's kind of interesting to see how the sources in the difference images move as you click on different positions here. I noticed this too, but it looks like maybe something weird happened with reference template subtraction. So some of these, yeah, there might be some of those um, maybe not super great difference images here towards the edges, which I think is just going to happen. Okay, so I mean, in these difference images, though, there's nothing super obvious, I would say. I think these are all very bright, so I think these sources here, there may have been some bad subtraction, or they're too bright to make any to and kind of cause some artifacts there. So nothing super obvious here, but we'll go through some examples of actual difference time varying phenomena. Okay. Uh, so yeah, okay, I'll pause here. Maybe if there's any questions on this. I see there's a question in the chat about if there are any important flags that are recommended when we want to exclude artifacts, bad weather. And then, okay, I see Melissa addressed that question. I think I also mentioned there's that use or that is dipole flag. So that's helpful for ruling out some artifacts uh, in the DIA source table is dipole. So you can do is dipole equals false, and then that'll help get rid of some junk. There's like extendedness parameters, I think, that you can also use to rule out anything that's extended. So I would recommend going through some of the flags and also going through the DIA source kind of level 200 tutorial that goes through some of the important flags that you can use to exclude any kind of artifact or and things like that. Okay, so let's move on to the second portal tutorial, which is here. And this one, we're going to use the portal to essentially plot a light curve. So this is plotting force PSF photometry of a specific DA object that we know is a likely supernova. It's actually the one that I showed in the beginning. So we'll just copy this, and then I'll paste it in the chat too, if you want to follow along. So copy that, and then we'll go back to the portal. And then to go back to that tab, we just click here, DP1 images. And then we have the text that we have from before, so we can either just clear it like that and then paste in our new query. So we're just grabbing the MJD information from the visit table and then the PSF difference flux from the force source on DIA object table. And we're just saying that we want to look at this particular DIA object, which we know is associated with this interesting transient. And we want to look at the band, at the R band filter. So we're only going to plot the R band's force source on the A objects or force difference PSF photometry from this target. So do that. And then on the bottom left, you can click search. And here's our light curve here on the right. So yeah, so that's one way to do a plot a light curve using the portal and that ADQL tool. And so you also see here on the table here all of the different all the properties that we queried using that search. So the MJD and the difference image flux here. So that's yeah, that's a demonstration of how to get a light curve using the portal. And then just keep in mind too, this since we did this query first on the left, I think that'll probably stay there, but it doesn't really have any association with this thing on with the plot that we just did. But if you wanted to, you could go back to that. Um, you could go back to that table by clicking this tab here. So I think it saves your searches if you want to go back and forth. So that's kind of convenient. Okay, so that's some of the portal demos and how we can like make light curves and look at DIA or difference images. There's lots of other things also that you can do as well with this, but those are just two very specific demonstrations of how to utilize the portal for kind of enabling or doing your science. What we're going to do next is we'll jump into the notebook aspect. So we're just going to look at two of the science demo notebooks that we've prepared to highlight some science use cases for extragalactic transients to kind of plot light curves and also to identify transients using different tab searches. There's also related or difference imaging and light curve notebooks related to this session here. I'm not going to go over them in this session, but if you have more questions specifically about these data products, difference images, DIA source, DIA object, force source on DIA object, like the question about the flags to use, I highly recommend checking these out, like the DIA source and DIA object tables and things like that for more detail on those data products. Okay, so for the last 12 minutes of this session 9, we'll go ahead and go to the notebook aspect and check out these science demos. So to do that, you can go back to data.lsst.cloud, and we're going to click on the notebook aspect here. So you'll do that. And then I'm already signed into it, so that's why this is popping up. But you have this, if you've already used it, you'll get to this landing page. If not, you'll have to click some different, um, let's see, the different versions to use and then which kind of container size. So you can click large and then go from that, and then RSP will load up and get started. But I'm going to go ahead and jump into this right away. So I'm going to go back to this window here where there's nothing loaded up. So to access the tutorials that we're going to go through, if you look at this tab up here, you can go to tutorials, DP1, 300 science demos, 306 extragalactic transients, and then 306.1 here. So it's kind of you have to, yeah, mouse cursor down a little bit. Um, but that's one way to do it. If you already had it loaded, you probably would want to overwrite it like this. And then we can do the same thing, DP1, 300 science demos, 306 extragalactic transients, and then 306.2. That's the other one that we're going to be looking at. And then I'm already in the directory that the demos or tutorial notebooks are loaded in, but uh, you probably your thing would look something like this. You go to notebooks, you have tutorials, DP1, 300 science demos, 306, and then here's where those tutorials live. And if you don't want to worry about having to do that again, you can copy the notebooks and then just put it in your home directory. So you don't need to go through this file directory navigation to bring it up again. Okay, so we're going to go through this one first. This is how we plot transient light curves. So the end product of this is essentially going to be part of what we already showed with the portal. Going to go through this a little more quickly to make sure we get to the second notebook. But basically, what we're doing is we're going to be doing a tab query of the force source on DA object table to plot the light curve. So first, we'll import the relevant packages. We'll start up the tab service. So I'm just doing a shift enter here to execute all these cells. This is just some functions to define plot markers and nice looking colors for making a light curve plot. And then this is where we're going to retrieve the light curve data here. So we're going to do that using the force source on DA object table because it has the force PSF photometry for all the difference images, not just the ones where there's 5 sigma detection. So all the difference images. This gives you the most information you want for your light curve. These are the relevant columns for plotting light curves. So PSF difference flux, you want to have the DA object ID, the band, which is the filter that's used in the observation, and also the visit ID. So that helps for doing what we call a table join when we're obtaining the light curve information or the date information from the visit table. So what we're doing is we kind of have an idea of we already a priori know where this transient is. So this is kind of demonstration about how we do that. One way to kind of do that using going by coordinates first. So this is a location of an extragalactic transient in DP1. So we can just execute that. We can define a 1 arcsecond search radius here. And then we're going to search this position for the DA object ID that corresponds to these coordinates. So we're just going to execute that query, or we're going to define it first and then run that tap query here in this cell. And the output of that search, we can save it to this DA object table, and it just tells you, like, yes, there's one DA object ID associated with it. Here's that object ID. And now we'll do another tap search. This is to obtain the light curve of this DA object. So we'll define what the DA object ID here is with this variable. And then we'll do another tap search, querying the force source on DA object table and the visit table. So we're doing this table join here because the force source on DA object table does not have the timing information. It does not have the MJD. So you need to use a common column between that table and another table with that visit information. So we do a join between the force source on DA object table, which has essentially the flux information, and the visit table, which has the timing information. And so that's why you can see here the viz dot exp midpoint MJD, that's the timing information. And then we're joining on the visit ID since that's in both tables. And then we're getting the PSF flux. So let's define the query and then we'll execute it here in this cell. And then we can see how many sources were, or how many essentially flux measurements were taken um, in that coordinate or in the DA object, and then we'll plot the light curve here. So there it is. That's the forced PSF photometry light curve of this extragalactic transient. And then you also see here that it goes negative, and that's because the transient was likely bright in the reference template image that was built. So when it fades below the reference flux value, it goes negative. Um, and so hopefully that won't be as much of an issue for actual LSST cam uh, data since there'll be a longer baseline um, for reference template building. This might happen a lot for a lot of the um, DI objects or a lot of the transients and variables in DP1. All right, so yep, again, yeah, kind of very straightforward notebook. This is how we recommend plotting a light curve for a transient or variable. Okay, so let's go to this notebook 3062. This one is a more a science. It's a more focused on a science use case of how do we actually identify transients that we might be interested in the DP1 data. So I'll go through this here. We're gonna do this notebook is fairly lengthy, so I'll kind of just hit the key points here. And what I'm going to do is I'm going to move this, and maybe this is a little more helpful for viewing uh, this page here, or at least in the screen share. So I'll execute this. These are just the different package imports, starting the tap service. And then we're going to use this simple image access service, or SIA, to obtain image cutouts. Again, the filter, colors, and symbols. and then setting the backend for our plotting. Um, this is, we can get a sample of, first we can get a sample of DA objects. So we'll use that same position in the ECDFS field and then do a 2-degree search of this field for all the DA objects in there. This takes a while, I think, to run, if I remember correctly, because it's doing this query at this position, looking for all the DA objects within a 2-degree search radius. So we can wait for that to execute. And yeah, I guess it takes around 15-ish seconds, and then it's going to also save the results to a table there. We can check out some of the characteristics or statistics of this table. Uh, and this ties into the question that Naoki asked earlier about like DIA objects and the number of DIA sources associated with it. So you can see here that the number of, in this histogram, the number of DIA objects that has NDIA source is 1 or very small is super, super high. And that's because a lot of these will probably be like junk or stuff that's artifacts, not real. So that's one way you can just cut out a lot of junk. You can do an NDIA source cutoff there. Same thing is true for this. This is just number of flux measurements at the R band. So if you want to do a specific filter cut, you can use um, this parameter there. Okay, this is just this plot here is just showing a histogram of the minimum and maximum R band PSF flux values and the linear slope. So we're using those to look for 1A supernova candidates. Um, so that's just some of the properties that we're using in the histograms that are shown there. And then to look for 1A candidates, we're putting specific, we're creating specific conditions that the DI objects must have, and we're considering those the filtered DI objects as part of our candidates here. So here's just some of the conditions that we're setting. We're saying that NDIA sources has to be greater than 5 to make sure it has like a good number of detections. We want it to be well below the saturation limit. So that's setting the mean flux below 10 to the 5.5 nanojanskis. We want more than 10 R-band detections. Um, and we are setting this uh, value here. So the slope is decreasing at a level between 3 and 7%, which is what you'd expect for a 1A supernova flux decrease at that part of the light curve. And then this here is just making sure that there is some amplitude that's observed from in the R-band flux so that it's at least 10% greater than the mean flux. And so we'll do that there. So that's the filter. There were like 200,000 DIA objects in the initial query, and then 13 1A candidates based on this filtering here. So we can plot the light curves. Let's see, which is just doing essentially what we did in this previous notebook, but for all of our objects, all of our DA objects. So here they are. This top right one should look a little familiar. That's our supernova candidate. And if you want to look into it in more detail, you can use use the alert brokers. I won't go into that in detail here, but this section here is for exploring that. And then since we're running a little short on time here, I'll just real quick show how you can actually get cutouts because, okay, it's cool that you can see the light curve, but we want to actually look at the data and see what it looks like to make sure with our eyes that we believe what's going on there. So I'm going to just execute these. This is essentially just using the SIA service to grab the science, the reference, and the difference image. So the science image, which is the visit image, the template coad image, and then the difference image there. So we need to do a couple steps. For example, we need to warp that template image to make sure it's in the same orientation as our science image, so it's in the same WCS. And then this is the product of that there. And then, yeah, if you want to, you can correct the typo there, do template. There we go. So that's our cutout triplet. That's what we started off with at the beginning of this session where I was showing you this here. So now you can do that and make a whole bunch of cutout triplets for any kind of interesting transient or variable time varying phenomena that you see in DP1. All right. So yeah, thanks everyone for your attention. We are like a minute over the end of our session. But yeah, thanks for sticking around, and I'm happy to stay around for another 10 minutes or so if people are interested, if people have any questions. Um, yeah, stop my screen share. So yeah, if there are any questions, feel free to either use the chat or um, raise your hand. Uh, yeah, anything at all. And if not, that's totally fine too.